All right, it is now time to get started with our keynote speaker. So I'll have Bob pop on in and share his screen. We are so pleased to welcome Bob Meadows, who is a physical scientist with the National Park Service Natural Sounds and Night Skies Division. His current responsibilities include managing the 19 years of sky quality data for more than 125 park units, conducting measurements and assessing sky quality in the field, and working with parks to evaluate their lighting for efficiency and ecological impacts to the nighttime environment. Bob also works with other partners in the scientific community in collaborative efforts to further mutual goals of restoration and preservation of our night skies. Bob has worked in the Night Skies program since 2011. Prior to that, his professional experience included almost 25 years working in Sequoia and Kings Canyon National Parks. Welcome, Bob. Take it away.
Thank you, Holly, and good evening, Minnesota. And happy to be here and give a little talk about what we do in the National Park Service to preserve and restore, as I say, and promote the night sky as a resource. As she said, I work in the Natural Resources Stewardship and Science Directorate of, it's a Washington, D.C. office, and it's actually based in Colorado. I'm in Fort Collins, and part of our office is also down in the Lakewood area of Denver. And we're one of several natural resource programs that are here in Colorado to support the National Park Service system across, all 421 units with expertise and assistance, especially with many parks who don't have that those kind of staff available. So again, I'm with the Night Skies program and part of the Natural Sounds and Night Skies division. And this program started quite a ways back, and I'll just initially touch on the origins of the program. So going back in the National Park Service, back in 1995, Dan DeRisco, who was a longtime coworker of mine at Sequoia before he moved on to start this program, he conducted the first night sky quality assessment at an NPS unit, and that was Oregon Pipe Cactus National Monument down in southern Arizona. And then about 4 years later, another NPS employee who knew both Dan DeRisco and Chad Moore and knew of their interest in night skies work and their amateur astronomy and things like that, connected the two of them together. And Chad and Dan realized they had a shared interest in preserving the night sky, promoting the night sky, and documenting the conditions in areas, primarily in the National Park Service, because that's where they both worked at the time. Moving forward about 4 years after some initial engineering and testing and actually data collection, they both actually resigned their permanent NPS positions, which is a pretty big step because they were well established with their federal jobs, but their desire to really pursue work and in the night sky world was pretty strong. So they took on temporary positions. Chad was really good at getting funding, and the Night Skies program, was born at that time. And initially, Chad was based at Bryce Canyon National Park, and Dan was at Death Valley National Park, two of the premier areas for night skies programming and quality skies. So that takes us to, what does the National Park Service have in place to address the night sky as a resource? It hasn't always been considered something that even employees or anybody else talked about. You always think about the wildlife, the geology, the water, the water resources, those kind of things. But night skies is never, at least hadn't been something that people openly discussed about. So come 2006, NPS management policies were updated, and Management Policies 4.10 addressed lightscape management. And what it said was, the service, being the National Park Service, will preserve to the greatest extent possible the natural lightscapes of parks, which are natural resources and values that exist in the absence of human-caused light. To prevent the loss of dark conditions and of natural night skies, the service will minimize light that emanates from park facilities. And they will also seek the cooperation of park visitors, neighbors, and local government agencies to prevent or minimize the intrusion of artificial light into the night scene of the ecosystems of parks. So we have this policy in place, and what is the National Park Service doing to address this policy? Well, that's where we come into play. And again, we're a small little group. There's 4 of us in our division that are dedicated to night skies, and that's pretty much it for the entire National Park Service. And it's hard to imagine. There's a few people out there at the parks who have some experience, especially giving programs and things like that, but not very few, if any, who have the capacity to do scientific measurements or anything. So what we did first, and what Chad and Dan initially wanted to do, was do an inventory, a measurement of sky quality conditions at parks. And their first goal was to go to parks where they believed that relatively natural skies still existed. So that took them to areas of what we call the Colorado Plateau, the Colorado River whole plateau that includes, Nevada, Utah, Colorado, New Mexico, and Arizona, places that are filled with national park sites, but also have an absence of large population centers, and they have dry skies and higher elevations. So it lends itself to quality night sky conditions. So they started with an initial inventory of sky quality conditions, not only at the Colorado Plateau parks, but some other areas. And we've continued that now for, going on 20 years. More recently, in the last, 5 to 10 years, there's been a lot of work from the international research community, as well as our program, in creating continental scale models of all sky brightness. And then another thing that we're doing is now developing methods and tools for measuring glare and scene luminance in parks. And that's really the local lighting that's happening, the local impacts that park visitors might experience when they're around buildings or parking lots or roadways or things like that. We're trying to quantify those conditions. We also provide reviews on park plans and compliance documents related to the night sky resource. Parks are always updating management documents. There's a constant stream of new developments, or both inside parks and outside parks, that parks look for guidance and consultation, and we have in-house expertise in order to provide that kind of feedback to them. And then especially recently, and this is becoming one of our primary efforts right now, is we're developing guidance on outdoor lighting retrofits and new installations, especially with the change to LED technology. And I'll touch on that a little more later. So first, that initial statement of establishing baseline quality assessments across the system. Well, Dan and Chad had to come up with a tool, and they spent a couple of years doing a lot of work and ended up developing a system that's pretty similar to what we have now. The cameras are a little newer models, and there's been some additions, but it's basically starting with a monochromatic CCD camera, and that's a charged couple device camera, and anybody in the astronomic community would be familiar with it. It's a very high resolution camera that's very sensitive. It actually has an internal cooler that we cool it to -20 C to eliminate noise and things like that. So that's the camera there in the upper left. We use this Finger Lakes instrument microline. We have a couple of other versions that we also have in our repertoire. In the bottom left, we've and about 3 or 4 years ago, we added a filter wheel to our system. We'd always had a filter on the lens when we were capturing images for the V band, which mimics human vision. But as LED technology came along, we knew we needed to start capturing the change to the fairly common blue-white spectrum of LED lights that wasn't being captured with our V-band filter. So we needed instead of a single filter on the lens through the whole process, we needed some way to rotate filters through. So we added this custom filter wheel that Finger Lakes Instruments adds, and that allows us to add a B-band blue filter. So we're actually taking images with 2 different filters on this. And on the right here, this image, this is basically our camera system out in the field at night. This happens to be at John Day Fossil Beds in Eastern Oregon, one of the premier sites if you ever have a chance to get out there in the high Oregon desert for seeing the night sky. I should say there's 10 of these cameras in existence, and 7 of them are within the NPS. 2 others, technically, we've helped with. One of them is with McDonald Observatory in West Texas. We've been helping them over a number of years with their efforts to preserve their night sky over their system. We have a cooperative researcher out in California who has his own, and Joshua Tree National Park and Carlsbad Caverns recently purchased their own systems. We still do the processing on that though. So there's more to it than the camera, though. To get all this running, it looks like a simple system, but we need a lot of these other components. We have a tripod. We use a Celestron telescope mount that many of you may be familiar with. We've modified the mount on the base and on the plate to adapt to hold our camera system. We have a little netbook computer, some lithium batteries, converters. We use GPS for precision coordinates where we are. So when we take the data, there's a precise point. Weather conditions with a Kestrel weather meter. We need to level it, all these kind of little things that come into play. You also might see an SQM, sky quality meter, there in the upper part. And just as a cursory measure, we take a sky quality meter reading along with all of our data each night we're out there. And just some more communications and power connections, a lot to it. We've actually narrowed some of this down, kind of refining our system, trying to make it as streamlined as possible because it is a little cumbersome at times. So with this camera, what we're able to do is we're able to collect calibrated luminance and illuminance data on a single image. So a single wide field CCD image of the night sky with an appropriate lens, filter, detector combination can be calibrated on known standard stars, producing an array of calibrated photometric data and giving a high resolution description of sky brightness. And I'll start from the left here. That's an image straight from the camera, and it's a 16-bit monochrome image, and that's everything that the lens sees from natural to artificial. And then in the next image, what we're able to do is real-time photometry using star catalogs, the Hipparcos star catalog Tycho 2, and we provide actual calibration using the existing star brightness from the catalogs. And then that calibration is applied to each pixel in the image, giving a brightness measurement or a luminance of that image. And then we apply a false color ramp to give a better depiction of what that actually looks like in a gradient. So the image acquisition process. We're using start this up. Again, we use a commercial Nikon lens. In our case, we're using a 50 millimeter lens. It's a 1.2 lens, but we set it at f2.0. We're using that V-band filter as well as a B-band now, and a research grade monochromatic charged coupled device camera. The V-band filter, as I said, only lets visible light pass through, allowing a detected signal to closely represent what the human eye can see based on our spectral sensitivity. So we really want to mimic what any of us would see out there to have that picture. And each image covers 24 by 24 square degrees. So what you're looking at here in this white kind of graph with all these numbers is the entire hemisphere from the true horizon to the zenith in the center. So we're capturing 45 images based on the width of the images, and each image is centered on one of these number dots. And I'll start a little kind of numbers. And this is how the camera goes around on the first level on the horizon, taking a picture. It raises up, it goes back around the other way, it raises up a little higher, kind of reverses itself, and then finishes off with about 5 images at the zenith. And all of these images overlap just enough to allow us to create a seamless panoramic image, so to speak, of the entire night sky. And this is the size of the image, 24 degrees by 24 degrees, 1.4 arc minutes per pixel. That little red dot you see in the upper left of the image there, that's the approximate size of the moon if the moon was in the sky. And we don't want the moon in the sky because that creates too much light for that. So we're capturing a lot of things with our camera. The first thing we're doing is measuring the nocturnal photic environment, and that's both luminance and illuminance. And there's established brightness values for Vega, and then we have things like the Milky Way, the natural air glow, the landscape itself. You know, sometimes the albedo of the landscape creates a brightness. And then we've got this measure of the natural environment. Then we want to measure the anthropogenic or human-caused light in the landscape. So measuring anthropogenic light may involve both illuminance and luminance measures. And the two most important targets that we're looking at are skyglow and light trespass and glare. And you may be familiar with skyglow, but skyglow is basically all light, human-caused light that's, you know, going into the atmosphere, be going down, sideways, upwards, and it scatters into the atmosphere and creates this glow or glare, not truly glare, but a glow. And sometimes it's pretty significant from bigger cities or very bright installations. And it depends, of course, on your distance. So this is what you might see, you know, from northern Minnesota. You might see this off in the distance towards Duluth, or if you're in central Minnesota, something like this if you're out at night from, you know, the Twin Cities there. And then on the right is something we're really concerned about at the park level, at the local level, and that's light trespass and glare. Light trespass is light that's going into an area that is not intended. An example would be you go and turn on your back porch light to see outside in your backyard, but that light is not shielded, and that light goes into your neighbor's bedroom, which is not an uncommon thing, or into their yard. So that light is trespassing. And the same thing could be said for going from one piece of property, you know, one industrial area, or even from our installations, you know, one of our facilities, and the light trespasses into the natural area. The other item is glare, and glare is kind of the invasive, the really difficult thing for both humans and wildlife to deal with, because that's kind of a thing that affects our night vision or our scotopic vision. There's two types of glare, both discomfort glare and disability glare. And just the slightest bit of glare at night can really disrupt and end your night vision for 10, 15, 30 minutes or more. So it's something we really want to try to capture. And let me touch quickly on the terms illuminance and luminance, because those could be confusing sometimes, but we use them a lot. Luminance describes the measurement of the amount of light emitting, passing through, or reflected from a surface from a solid angle. So kind of the glow, what you perceive as the light from some object. Illuminance is a term that describes the measurement of the amount of light falling onto or illuminating and spreading over a given surface. So that's light striking a surface, whether it's a horizontal surface or a vertical surface. So we've captured, you know, all the different lights in there, both natural and artificial sources out there. And for this example, I'm using some data that we collected up in Rocky Mountain National Park many years back. And this is from high up on Trail Ridge Road, if any of you are familiar in Rocky Mountain, at about the 10,000 foot elevation. And this is, again, in the monochromatic world, and you're seeing both the landscape, because where the camera was set, some of the features are above the true horizon, and you're seeing down into the lower elevations, and that is actually the Front Range cities from Denver up to Fort Collins and all that area. And we take this, and you know, we've now stitched all 45 images together. We have this complete picture of the entire night sky from horizon to zenith. And then we apply our false color ramp, a logarithmic scale of color to that. And we have this, you know, again, a better depiction of how the sky brightness changes over time. So next we take that and we reproject that into, we're using a Hammer Atoff equal area projection. And that means that any portion of this panoramic image you're looking at is an equal area representation. There's no stretching or compressing of this image. Everything there is an equal part of the sky. You're looking at 360 degrees across the bottom, and sometimes we'll project it a little different. Here we have due south in the center. It depends when we're trying to present, different information. Maybe light domes are predominantly to the side. We'll change that. But you've got 360 degrees across the bottom. And then you can kind of see we have a 30 degree, a 60 degree, and then at the zenith top center is 90 degrees or directly overhead. So this is the standard product, graphical product that we produce for an image, kind of depicting the sky quality. And this is all sources on that. This image alone is a valuable tool for assessing sky quality within a park, but because it's a calibrated image to standard stars, we can also pull out a suite of metrics. In order to quantify anthropogenic light, however, we need to know the natural sky brightness. So Dan and his amazing brain and infinite wisdom was able to build a natural sky brightness model based on a lot of data that he had collected over time. And Chad was also involved in this, both brilliant individuals in developing this early technology. So the idea is we want to build a model of all the natural sky so we can subtract that from the all sky images. And the primary components of the natural sky are air glow. And air glow is the emission of light from chemical interactions between oxygen, nitrogen, and other molecules in the upper atmosphere, typically around 90 kilometers above sea level. And air glow is very, it really reacts to high solar activity. It's something that's not easily seen with the naked eye unless you're practiced or you know what you're looking for, but a lot of times it presents itself as this kind of green glow on the horizon. It could be banded too, which is difficult to subtract. There's some amazing images from the International Space Station that astronauts have taken showing the band of air glow over the Earth. So that's one of the components. We have the atmospheric diffuse light, that's integrated starlight, just basic background of the universe out there. Of course, we have the Milky Way, which is where we're located within the Milky Way, not always up, depending on when we're collecting data. And then we have the zodiacal light. And the zodiacal light is sunlight reflecting off comet and asteroid dust concentrated in the plane of the solar system and best seen after sunset in the spring, that would be in the western sky, and before dawn in the fall in the eastern sky. And if you're in a darker area after sunset, when you're getting towards astronomical twilight and you look off to the west-northwest, sometimes you'll see this almost really bright pyramid of white light, and that's the zodiacal light, very prominent in some places, pretty unique. And that's another thing we need to do. So we get all four of those and we create a modeled sky luminance, and that's a picture of that. And then we get back, and below it is, this isn't that rocky, but this is the observed sky luminance in a spherical projection here. And the same data that those, that model sky was. And the planet Venus is present in the night sky. Obviously, it's the brightest object outside of the moon. And we want to remove that. It's just a little bit too bright. And we have some scripting that allows us to put band-aids or patches over some of the brightest objects, such as a few planets and things like that. And then we also mask out, some feature like that antenna. So that then gives us a natural sky model. And this is only the natural sources of the sky in this same projection, this Hammer-Echthoff projection. We take that information, we subtract it from the all sky sources, and here is what we're trying to get at. This is the anthropogenic or artificial human caused sources only Mosaic. And this is again from Rocky Mountain National Park. And this is what we use to kind of show the impact of the non-natural sources on a particular location. In this case, the observer from this spot, this is what they're seeing. Very bright for these areas from Denver through Longmont, Loveland, Fort Collins, and other places. But still, if you look at the zenith, it's still in a natural condition. And if you were to turn your back to that location and look, towards the west, 270 degrees on the right side of the image, you're almost getting a completely natural night sky. So there's a lot of that if you're not surrounded by light on the horizon where you have the opportunities. And the number there at the bottom I want to talk about is a metric we call the all-sky light pollution ratio. And what that indicates is the ratio of artificial light to natural, or the condition above natural. And that's what we consider to be an excellent indicator of sky quality. And in this case, for this location high up in Rocky Mountain National Park, the ALR is 0.53, or in easier terms, it's 53% brighter than a natural sky. And that actually is not too bad. That's fairly good. There's not a lot of places that you can get out to that have a sky quality better than that. There's still detail in the Milky Way. M31, or the Andromeda Galaxy, can be seen. However, the Denver Light Dome casts shadows. From this site, though, you're not seeing it here, but 4,000 stars are still visible. And the darkest portion of the sky is less than 10% brighter than natural conditions. So that 53% is kind of a mean across the sky. But if you were to look at the core of the Denver Light Dome, that's 4,000% brighter than the brightest part of the natural sky. So some things to think about. And we have a lot of these measures and numbers in the astronomical world, and some of them engineers use, some of them astronomers use, and it could be very complicated. It still is for a lot of us. Photometry in astronomy. One of the most common measures is something called the astronomical magnitudes. And as it says, this magnitude scale dates back to around 100 BC, and this peculiar system is a logarithmic scale, or logarithmic ratio, with 0 based on the star Vega. So that's kind of your baseline there. And every 2.5 steps on the magnitude scale is a 10 times difference in brightness. So if you were to go from magnitude 7.0 sky, which is getting down to the threshold of what people, their visual systems can see, and you went to a 5.0 sky, the sky is 10 times brighter. And then if you went to where the darkest star you could see is a magnitude 2.5, you're now another magnitude of 10, or it's 100 times brighter than it was when you could see that 7.0 magnitude star. And the magnitudes are given in the Johnson UBVRI system, UBVRI standing for ultraviolet, blue, visible, red, and infrared. And this magnitude scale allows us to easily compare well-known astronomical objects to anthropogenic sources of light. So as I mentioned, we are able to extract a whole number of metrics from the data that we collect, especially after we've subtracted. And generally, we're reporting out to our Park Service units when they're asking for information, kind of a small subsample of those indicators, which we think is are most valuable for their management. And we have both sky luminance measures and illuminance measures. And left to right, we have the indicator, the observed measures, the estimated artificial measures based on our subtraction of the natural sky, and then that all sky light pollution ratio. And then, we're looking at the zenith, the mean all sky, the brightest point of the sky, the darkest place in the sky, the median for the whole sky. And then for the illuminance measures, what we consider very important indicators or things to look for is that horizontal illuminance and that vertical illuminance, especially the vertical illuminance. As for humans, we spend most of our time upright, especially moving around in these parks. And it's that light that's striking that vertical plane that really is something that causes us a little bit of grief. And that's where most of the light, unfortunately, is coming from, either the distant horizon or on the horizon. It's generally not straight up in the sky unless you're under some kind of parking lot light or something like that. So we've been, collecting that data, and let me give you a summary of what that means and what that looks like since 2001, when Chad and Dan first started up with their first camera system and started collecting data, going on 20 years now. Unfortunately, this year, we really haven't been able to collect almost any data. As you well know, nobody's been going out and doing things. But to date, we have over 500 nights of usable data at approximately 130 National Park Service units. That's out of 421 that are currently in existence. and about another 57 at non-NPS locations, such as Forest Service lands, Bureau of Land Management places, state parks, et cetera. And a lot of times those places have interacted with us, they're familiar with our work, and they've had some needs or requests for us to come and collect data. Some other times it's been advantageous for us to collect data. Maybe these sites are immediately adjacent to a National Park Service site and provide a better location. We're collecting these high resolution all sky images of both observed sky brightness and derived artificial sky glow are produced. A suite of indicators, as I showed on the previous slide, is produced and stored in a relational database. And then that data is currently available on a public website for about 2/3 of the data, but it will very soon be available for all locations, all of those 500, actually 557 nights on our NPS website. And that information down there will take you to our current website and get you to the available data. And anytime you just type National Park Service night sky, it'll lead you to this. So a lot of nights, a lot of data nights. There were actually a lot more data nights out there where we weren't successful, either from clouds, equipment failures, just a number of other things, processing things. It's a very complicated collection and processing script. So no guarantees on that. And first and foremost, we need clear, cloud-free skies and not too windy. So it's not an easy thing to find those nights. You have about 13 to 15 nights a month where you don't have the moon in the sky. So kind of limits our abilities. And here, I'll just show you kind of just a sampling of our camera out in the field, just to give you an idea. We have really, it's an amazing job I have and my coworkers and of course, Dan up in the upper right, Chad there in the bottom center, the places we've been able to go and collect data. Sometimes it's not easy. Sometimes you're carrying, 40, 50 pounds or more on your back and you're working at night. But the places we get to go are pretty spectacular. We have places like Alaska in the upper left, North Cascades in the upper right center there is the Florida Everglades. Bottom left is actually Mauna Kea, the summit of Mauna Kea in Hawaii, adjacent to Hawaii Volcanoes National Park, where all the observatories are. Florida, again, so just a variety of places. And just to show you on a map, this is a distribution of all of these are National Park Service sites where we've collected data. I don't show the non-National Park Service sites on here, but this kind of gives you an idea, and I don't know if you could see my mouse here, but this is what we consider the Colorado Plateau, the heart of the Colorado River, the high dry areas, low populations, and lots of national park units. And initially, this is where Dan and Chad focused their efforts and kind of this area, and you saw a lot of data collection. But they also, went to places in California and up into the upper Rocky Mountains and even a few places out in the Northeast. And since then, we've really tried to spread ourselves out, and we've had a lot more national park units request our services and request baseline measures to get an understanding of what their sky quality conditions are. And since then, we've gone to Florida. We've hit a lot of the Florida parks and the East Coast parks from the Outer Banks and the upper interior of the Northeast U.S., as well as a number of parks in the Great Lakes, including northern Minnesota and Lake Superior area. And we've probably got another 25 or 50 parks, I imagine, over the next 5 years to 10 years that probably would be interested in or would benefit from these type of all sky measures. As you could see, we've also been to Alaska, which is extremely difficult because they have only the winter time when the night sky is out, and obviously conditions are pretty harsh. I was out collecting data at Yukon Charlie Rivers a few years ago with a coworker, and it was 35 to 40 degrees below zero in the middle of the day, which constituted about 3 hours. So pretty difficult conditions to try to capture something. And up in Alaska, as you can imagine, the aurora borealis plays havoc with us, as does it in places like Isle Royale and even Voyagers at times. So Hawaii, American Samoa, and the South Pacific, and Virgin Islands. So we're pretty well out there across the system and across the U.S. And then I wanted to show you kind of a range of the sky quality, showing that same type of panoramic image of conditions that we capture and that you might see as you go places around the US, not just national parks, but I'll use national park sites as an example. From the upper left here, we have Glen Canyon National Recreation Area along the historic Hole in the Rock Road that the Mormon settlers used back around 1880. And this is in the heart of central southeast Utah, and Glen Canyon National Recreation Area is a vast NPS land. And this area is almost devoid of any anthropogenic light or sky glow from any communities. If you really squinted in the right center bottom, you might see a little dome, and that's a very distant community on the Navajo reservation in Arizona called Cayenta. Otherwise, that's fairly close to a natural sky out there. Going down, we have close to home for many of you, the Apostle Islands National Lakeshore, and this was taken from the outer island sandspit. I think it's the northeastmost island in the park, and fairly removed from any cities or communities. And again, an excellent night sky. Just the hint of a few developed, cities or towns off in the distance in Wisconsin there. Getting a little brighter, we have Acadia National Park from Cadillac Mountain in Maine, still unaffected at the zenith. Lots of people go to Acadia for night sky festivals like this one. Moving down, getting a little brighter, we have Pinnacles National Park out in central California towards the coast, and you start to get the influence of the big cities such as the San Francisco Bay Area and the central San Joaquin Valley, and starting to have that entire sky impacted by the sky glow and brightness. And then moving to the upper right, we have Channel Islands National Park off the coast of Southern California. The islands themselves, there's literally no development, no lights or anything on the island, but their proximity to the coastal populated areas from the Ventura, Oxnard area down to the greater Los Angeles area. And you could see that incredible brightness. And really, there is no natural sky left there on the Channel Islands, just because of its proximity to the greater coastal areas of Southern California. And then we'll move down to the southeast coast of Florida to Biscayne National Park in Biscayne Bay, an amazing marine sanctuary area, but its geography has Miami and the greater Miami area going to the south directly across the bay. And it's pretty significant. I was out there, that looks like 6.5 years ago now. And the brightness is pretty amazing. On the far left there is actually a large power plant. And then you move over towards the center of the image and you get the core of Miami, the city of Miami. But I did know that when I turned my back to all that and looked to the east out over the Atlantic Ocean or towards the Atlantic Ocean, I was still able to see quite a few stars and even a little semblance of the Milky Way. With a little bit of time not looking at that. So there's still little opportunities. And then we go into this next one, getting extremely bright. And this is Morristown National Historic Site in New Jersey, maybe 50, 75 miles west-northwest of New York City and the populated areas in New Jersey. And as you can see here, the sky is very bright, not completely washed out, but very difficult to see any kind of celestial features. And then lastly, is Rock Creek Park in Washington, D.C., which actually they have a planetarium there. But if you were to stand there at night, you would struggle to see anything more than, Venus, Jupiter, maybe Sirius, and a few other brighter stars. The sky is completely washed out. So quite a range just in the NPS. And you'll see a similar thing. By no means are national parks the best places to see the night sky, and they don't obviously have the worst, but they provide opportunities for people to get out and experience a night sky that might be better than where they live. I'll take you a little closer here and just give you a quick example of some data we collected. This is from 8 years ago. We've actually had some more recent data, but this was really good information about 2012 from a couple places in Voyageurs National Park. If you haven't had a chance to get up to Voyageurs National Park, spectacular place, both daytime and night. And Voyageurs has been very active in recent years in working to protect, restore their night sky resource and really promote that as something that people can experience. And this top image is taken from the Rainy Lake Visitor Center, and that's about 18 miles east of the community of International Falls. And then the bottom one is taken from an overlook, and this is in the Ash River area of Voyagers, which is about 46 miles distant from International Falls, and not a lot else. They look a little different, and you might think that the Rainy Lake Visitor Center is a darker site. That's really a factor of atmospheric conditions and a little more moisture and what we call extinction. The forest overlook in the Ash River area is pretty spectacular, and even further away. To give you an idea, that kind of glow you see at the bottom of the Milky Way in that top image is International Falls. In the bottom image, it's just a different time period, and the Milky Way is not quite lined up. In that same area at about 280 to 300 degrees azimuth on the right side is International Falls, and you can see it's a little fainter. Both of these, though, have an all-sky light pollution ratio of only about 10% brighter than natural, and that's excellent conditions. So that really provides people with the opportunity to experience almost a natural night sky. So I will just show another bit of data that my coworker collected about 3 years ago when she came down to do, or she flew out to do a presentation during the Celebrate the Night Sky Week that the International Dark Sky Association Starry Skies Lake Superior chapter put on in Duluth. And she gave a talk on some of our technology. And she was asked if she can collect some data in the Duluth area, just as kind of a picture into what it is, comparatively to some of the other areas. And not trying to pick on Duluth we could do this for any community, including Fort Collins, where I live here, and anywhere else in the US. They just happen to collect data. And this is kind of east-northeast Duluth at the Hawk Ridge area, which I believe has some astronomy programs and is used for this type of discussions and talks. And you could see that, the sky is very bright from the core of Duluth, and it's brightened all the way up to the zenith there, but there's still opportunities to see the night sky. It's not as exaggerated as this image shows. So that's kind of an overview of our data. Another thing I talked about earlier was the modeled data and what that provides when we can't get out with our camera. Going way back over 20 years ago was the first World Atlas of Artificial Sky Brightness was published. And this was published by a couple of researchers in Italy named Pierantano Cenzano, who created a model, Fabio Falchi, and then also was Chris Elvidge, who is a researcher with NOAA here in the US. And what they did is they took satellite imagery. At the time, it was defense mapping satellite imagery, which was a little coarser, of the Earth at night, just looking at light as it radiates upward. So nothing going sideways or anything else. And this is over a period from 1996 to 1998, gathering cloud-free composites. And then they introduced the concept of a ratio of artificial to natural as an indicator of sky quality conditions. And this was their first thing. This was published in 2001. And using that base and taking some other information and putting into models, they both went backwards and forwards. So what they did here was show what the conditions were based on information that they had in the late 1950s for the continental US. And as you could see, still fairly good. Very few areas aside from the northeast corridor where light is very pervasive and just across the landscape. The greater Chicago area, obviously, in some of those other places, and the west coast of Los Angeles, San Francisco, Portland, and Seattle. But otherwise, vast areas of the western U.S. and even southeast and central U.S. where there was very little light on the landscape. Well, let's move to the middle 70s, and you could start to see that change happening, especially across the eastern U.S., as more and more outdoor light happens. And obviously, this follows, population expansion into the landscape and more use of outdoor light on that. And then it brought us to 1997 when they first captured the data, and you could see things have really filled in the Northeast and the upper Great Lakes and on the West Coast. And then they looked at that time about 23 years into the future, which is now only about 4 years into the future as we look at this information now for 2025. And their predictions based on that initial model are not too far off. And unfortunately, it's not a pretty picture for those of us who like to have places to go to see the night sky. So reality is it's there. What's happened since then? A few years back, Fabio Falchi, and he joined with Dan Dorisco from our original founding team, and they revisited this First World Atlas and created a New World Atlas of artificial sky brightness. And what they did, in addition to using new high-resolution imagery, the VIIRS imagery that's captured from satellites at night, they also used ground-based measurements as an input. That really kind of gave a better accurate reading of what was going on. And that produced a model that's still fairly similar, but much more refined to what was predicted for 2025. So the best thing I could say about this, everything out there, that impact on the lightscape and the nighttime environment is unlike a lot of other resources that are permanently, altered and can't be restored. The night sky is up there exactly as it was 50 years ago or 500 years ago or 5,000 years ago. It's just being masked by our light at night. And it's behind there. And if we provide opportunities and places to kind of hide that light or turn it off temporarily, you have that same night sky that, our ancestors were seeing. So that's the positive I want you to take out of this. We haven't lost it permanently. We've just temporarily lost our ability to experience it. So we have a lot of challenges to the Park Service, a lot of them from the outside. I'll quickly go through this. This top image is a panoramic taken from Saguaro National Park in southern Arizona. And what you see there is the city of Tucson, approaching 1 million people. This image, I will say, is taken before the city of Tucson has done some significant retrofits to their lighting in the last few years to really improve things. And the city has a pretty aggressive lighting ordinance, realizing that the night sky is important. There's a number of astronomies, not only in Arizona, but in the southern Arizona area that really depend upon their ability to see the night sky and not have that sky glow wash out their sky. So they're working towards it. And if we were to take this same image today of Tucson, I would suspect that we're going to see a much better conditions. It'll still be a large city. The image on the bottom is taken from Joshua Tree National Park in Southern California in much the same way. This is looking across the Coachella Valley, which is about 100 miles east of downtown Los Angeles. And what you're seeing from right to left are the cities of Palm Springs, Rancho Mirage, Palm Desert, and Indio. Some of you may be familiar with that. And some of these areas are obviously very bright and light up the mountainsides of Joshua Tree National Park on the south side. These challenges to the parks don't come from the outside only. They are from the inside. And this is a place that most people recognize, the iconic Yosemite Valley. And this is a beautiful image a photographer took at night from Glacier Point. And this image of the Yosemite Valley emphasizes the glow from the park facilities. As you look at this, you could see, I can kind of go around here again. This is kind of the main village of Yosemite Valley. You have Curry Village down here. You have the Ahwahnee Hotel development over here and some outlying infrastructure and, park roads and lights. But what's really evident from this image is how this light, which isn't shielded downward and contained in the area and is way too bright, is lighting up the iconic cliff walls, granite walls of the valley. And a lot of wildlife depends on, those places for habitat. Also, it's just, that light is being wasted. So the Park Service is every bit as guilty as places from the outside. And I want to show just some quick examples of, what we're seeing. This is from a park in Western Oklahoma, a historic park. And these are some new installations of LED lights that they found that somebody had purchased a few years earlier, mounted up on the roof. All good intentions, must be good. It's LED lights, but unfortunately they were pointed sideways. Their intention was to light up this little sidewalk, which surrounded the visitor center administration building at night. It really didn't get much use in reality. these lights, one of these blasted a neighboring ranch who quickly complained about the light. The other one actually shined about a mile away and actually lit up and created shadows in the historic battlefield that this park was there to protect and interpret. So another thing I want to show here, you've got two little bushes underneath this left light. If you look real hard here, my coworker, Damon, is standing in the middle. This is another example of what glare does. And if you ever want to talk about safety and security, this creates pockets of really dark areas where you can't see anything. So it's proper use of lighting, put it on task, things like that. Another example, quick example, this is at Cape Hatteras on the Outer Banks of North Carolina. Right along the shore, this is a Park Service parking lot, unshielded lights just blasting not only the people in the parking lots trying to move around, but obviously the coastal shoreline where the park is, prime habitat for endangered sea turtles. And one more very unique one. This is up in North Dakota at Theodore Roosevelt National Park. This is actually a single flare from oil and gas development that kind of cycled on and off about every 7 to 10 seconds and cast this incredibly bright glare and lit up this entire area that actually was Theodore Roosevelt's homestead in the Elkhorn Ranch area back before he became the president, and kind of developed this preservation ideas in the future. So a single light to many lights can cause many things. Fully sustainable outdoor lighting. I want to quickly touch on this. These are what we call our 6 principles of outdoor lighting. Light only if you need it, light only when you need it, light only where you need it, shield it down and direct downward. Use an appropriate spectrum for the task, and that's the color of the light, color temperature, warm white if possible, or amber lighting even more if you don't need real definition or depiction of colors. And then use the minimum amount of light necessary, and of course use energy efficient lights, which LED technology is. Because we're looking to kind of hit that sweet spot for full sustainability between the social aspects, the economic aspects, and the environmental aspects. Here's an excellent example. This is in Big Bend National Park in Southwest Texas, one of our best night skies if you ever wanted to experience it. And this is the lodge after it was retrofitted with lighting. Almost no impact to the surrounding environment. Everything is there. The lights are just on task. Those little bollards on the pathway are 1-watt amber LEDs, just fabulous work. And this shows you what it looked like looking down into the basin from Emery Peak prior to the retrofit and after the retrofit. And you could see how the surrounding mountains were lit up beforehand, and afterwards there's just a faint glow down in the valley and everything else is natural. This is what we're trying to do in the national parks. Here's another example from Death Valley National Park. In the Stovepipe Wells area, the Stovepipe Wells Motel, before and after, the lights that haven't lit up all the trees in the background, and they don't, they can't be seen from 30 or 40 miles up the valley across the barren landscape. We don't want to do harm to the surrounding environment. The iconic Lexor beam in Las Vegas with its light trap for insects and birds and bats, very bad. Can be seen from hundreds of miles away. In the center, the ideal hits the sweet spot. That's a housing outdoor light in Natural Bridges National Monument in Utah, just enough to see the pathway to the front door. And then the classic yard light or barn light on a maintenance facility. It's cheap to install and maintain, but it's expensive to run dusk to dawn, and the environment is poor. The utility is marginal because of glare. One more example of this: more light is not always safer and secure. This is taken at a university. You could see the individual on the sidewalk here, but a very bright overhead light, not evenly cast, way too much light. That person's still in this image, and she just moved 6 feet over, and she's standing under that light pole. Again, you've created real heavy shadowing. The idea is to reduce the contrast. Use appropriate lighting. Here's some great examples, from bollards to parking lot lights to wall lights to even historically cultural match lights. In the end, if you don't need a light, let's always turn it off when possible. And it is very important for us in the National Park Service to understand this, because darkness is habitat. Roughly half of all the wildlife on the planet is nocturnal. Darkness can be a critical habitat element. Artificial light affects the predator-prey balance, the migration, chronobiology, which is the natural physiological rhythms, and both skyglow and glare can disrupt ecosystems. Fortunately, the night sky has been in, the news, both publications and media, magazines. It's getting a lot of talk, and that's what we like to see. It's also very important to parks and communities around parks because of its stargazing and tracking, those kind of things. So dark skies are important for stargazing. It's often the most popular ranger-led event, especially in the Western US. It increases public interest, and it's an economic force for these communities around parks. Attending a stargazing program turns a drive-through park visit into an additional dinner, breakfast, a lodging revenue for the local economy. So something to think about, and a lot of communities around parks are really embracing that. Lots of events that have attracted thousands and thousands of people, if not more. We had a total lunar eclipse 6 years ago. Spectacular. This is taken from my coworker, Jeremy. And then, of course, 3 years ago, if any of you had the opportunity to experience the total solar eclipse, all of our parks, there was about 18 right on the path of the eclipse, experienced their greatest attendance ever in a single day. It was overwhelming, as were any other places along that. And don't worry if you missed that. In 2023, October 14th, and April 8th, 2024, 2023 is an annular eclipse, but in 2024 is another total eclipse, which actually is going to be twice as long, and it'll go from Southwest Texas, arc up through the St. Louis area over towards Cleveland, Buffalo, and exit out through New England. And if you haven't seen this, there's nothing that can prepare you for watching that total solar eclipse happen. I thought I was prepared, and still it was amazing. So I'll finish it off here with just some examples of some imageries in our national parks taken by coworkers and others, just to kind of give you a flavor for what we're trying to preserve here. Here's the racetrack playa in Death Valley National Park, the summit of Mount Whitney, the highest point in the lower 48 in Sequoia, Mesa Arch in Canyonlands National Park, Mitten Park and Dinosaur National Monument in Northwest Colorado, Black Canyon of the Gunnison National Park, again in Colorado, Crater Lake National Park out in Oregon. This image is taken from the summit of Mauna Kea in Hawaii. Similar view would be had if you can get to the top of Mauna Loa in Hawaii Volcanoes National Park. Not too far apart, but much more difficult to get to. And both Jeremy, who's the true shadow, and Dan, the ghost shadow here, have both said of all the places they've ever been, this is the most amazing night sky they've ever seen. And that's, again, it's at 13,800 feet in the middle of the Pacific. So anybody ever has the opportunity, that's a place to go. Here was somewhere that I was with Dan about 4 or 5 years ago, again, out in Canyonlands. Just the color was fairly similar to what this camera sees, remote area of Canyonlands, and then finish it off with a view from Trail Ridge Road in Rocky Mountain National Park. And with that, I'd like to thank you for your time. And I want to say, remember to enjoy the night in your national parks and anywhere else you might be.
Awesome. Thank you, Bob. Everyone at home, I hope you're giving Bob a good big round of applause for such a really interesting presentation of your work with the National Park Service.
Thank you.
So thank you. I am mindful of the time because we want to stay kind of on track, but I do think we'll ask maybe a question or two. And I should say, let our audience know that Bob will be sticking around for a panel discussion. And so I really appreciate all of the questions that have been coming in the Q&A box. And if we don't get to them right now, I'm hoping that we'll have the opportunity to wrap those into the panel discussion. So one of the questions I had for you, Bob, as you were closing, you were talking about the summit of Mauna Kea and recommending for people to go. Is that the most spectacular view you've had? Like, you've visited a lot of parks. One of our viewers asked, how many parks have you been to measure sky quality? And then maybe on top of that, what was the most spectacular place that where you've done your research?
Yeah, and I get that question a lot. There's, what's the best place to see the night sky in the national parks? Where have I seen it? I've been up to the summit of Mauna Kea, but I have not been there at night. So I did not experience that. For me, I've been to probably collecting data as part of my job. I've probably been to somewhere around 70, 75 national park sites. I've been to quite a few more in my own time. I would say there's quite a few. It's hard to narrow it down, but there was a particular night out in Death Valley National Park in the northern part of Death Valley, at a place called Saline Valley. And I was with Dan Dorisco at the time, and the temperature was extremely cold. It was, it was in the teens, very cold for Death Valley. Hard to imagine that, but it was in December, and all the conditions were lined up, and it was the most spectacular night sky I've seen. Had some hot springs there to adapt with, and that really helps your night vision adapt. Dan at that point saw the darkest or the faintest star he has ever seen, and he has very good vision. His training in that, so he actually saw a star down to magnitude 7.6. The zodiacal light at the beginning, everything about that was just spectacular. But I've seen places in Utah. Again, John Day, Alaska is unique. There's no light pollution to a lot of those places, but it's a different sky when you have snow on the ground. It's hard to really say one particular place, but I'll say that night in Death Valley was pretty amazing.
It sounds like it. Sounds like spectacular. So you had shared, another one of our viewers, Ben, was asking if these inventories are publicly available. And at some point in your slides, I think you listed a link. So maybe that in the window, you might be able, the chat window, you might be able to share with everyone what that link is for the publicly available data. But I was wondering sort of who besides the Park Service is using that data? And maybe could you give an example of how that information is being used to understand maybe the ecological impacts of light?
Yeah, absolutely. Outside the National Park Service, the international research community has been utilizing our data as kind of baseline conditions to develop new tools, and using ours kind of as the gold standard to see if they could create more simplified, less expensive devices to measure the sky. Perhaps they're trying to do an all sky, but we collaborate with quite a few researchers, particularly in the European community. Connie Walker there in Australia, a lot of individuals look to the data that we're collecting and producing papers based upon some of the information. The parks themselves are using it right now for management purposes, but we do want to make it available at all levels, not only the kind of the pretty products, the graphics, and some of these snapshot reports, but the raw data, everything we actually collect. It is the public. It's in the public domain because we're using public tax dollars to collect it. And as I said, that at one time snapshot from about 2015, we presented about 2/3 of the existing data then, and I'll put that information in the quick link to our website for people to go in, and it's actually on a Google Earth site right now. It's not a NPS site, but it'll give people an opportunity to kind of go around to different locations and see what the quality was. Okay,
that's awesome. Well, thank you, audience members. I see your questions. I've read your awesome questions, and I'm hoping that we'll be able to get to those very, very shortly as we move on to our next segment. So thank you, Bob. We appreciate you being here tonight and sticking with us throughout this evening. So as we transition, I'd also like to just give a shout out of gratitude to our many partners around the state of Minnesota who have been working with us to make our virtual statewide Star Party a reality, that they've done a fantastic job rallying audiences and students and stakeholders to make this statewide Star Party a success. And so I just want to give a shout out with logos there and say thank you.